be talking about matter. Now there's a lot of different parts of matter that we have to be concerned with. So this video is going to be a little bit long, but hopefully I can say it as quickly and as clearly as possible. So first what we want to talk about is what is matter. Matter is anything that takes up space and has mass. So everything that you see around you has to have matter because it takes up space, and if we were to put it on a balance, it would have some sort of mass. And again, mass is just the measurement of the amount of particles inside a substance, not the weight. Weight is something with force, which we're not going to be dealing with in this class. So we want to talk about the different states of matter. So we have solid, liquid, gas. You guys all know of those. And we also have something called plasma. We're not really going to be concerned too much with plasma, but know that it is a state of matter. So let's focus on solid, liquid, and gas. Now I just drew up little diagrams here to show you what the molecules in solid, liquids, and gases look like. When we talk about a solid, we have all of our molecules really condensed down close to each other. We do have a fixed volume and shape, so that cannot change for a solid. And particles are really, really close together. They're not moving very quickly. They're really not even moving at all. They're just vibrating back and forth. Now, as you add some heat, our solid molecules, they're able to separate a little bit and they become a liquid. Now, our liquid still has a fixed volume, but the shape is not fixed anymore. It takes the shape of the container that it's in, and the particles can now slide past each other. Then as we get to gas, we're adding even more heat. The more heat you add to a substance, the quicker those molecules can move. So here we have our gas molecules all spread out. Gases do not have a fixed volume or shape. They move rapidly. They bounce off each other. They bounce off the sides of the container. So that's solid, liquid, and gas are different states of matter. Next, we're going to talk about matter composition. So we have three different compositions that we're going to be talking about. We have elements, compounds, and mixtures. Now they're going to be broken up into two distinct areas. So elements and compounds are going to fall under pure substances, and mixtures is just going to be mixtures. So let's talk about pure substances first. So like I said, they're elements and compounds. Element is when you just have one type of atom. So for example, if I'm just dealing with aluminum, it's just going to be Al. All the atoms within the actual piece of aluminum that we see, that is going to only be aluminum atoms. There's nothing going to be mixed in with that. Another example is sodium. And here we have Br2 and O3. So when we have Br2, yes, we have more than one element that is there, but they're the same type of element. So it's the same type of atom. So this altogether is going to be called an element. Br2 is going to be known as a diatomic element. There are 7 diatomics that we need to learn. I'll write those out for you. Bromine being the first one. So we have now remember, you hear me say Brinkelhoff, that's the way I remember them. If you spell out that funny word or sound out that funny word, it gets all of your elements. So Br2, I2, N2, Cl2, H2, O2, F2. You need to know all of these. Basically, a diatomic element is saying that whenever it is not in a compound, and I'll talk about what a compound is in just a second, they have to be paired with one another like itself. Okay, compounds. Now we have 2 or more types of atoms chemically bonded together. So examples of this are going to be carbon dioxide, NH3, H2O. Now if we look at the difference between something in our elements versus something in our compounds, notice how we only have one element. Okay, we only have one type of atom, so we have aluminum, where here we have carbon and oxygen. So you have multiple types of atoms bonded together. We know that they're bonded together because when we write them, we're writing it together, not separately. So basically, whenever you are looking at a chemical formula, that's what this is, you'll know that there's an element if you have more than one uppercase letter. Okay, so here, C and O are both uppercase, N and H, and H and O. Now, something that stands true for all pure substances, whether it's an element or a compound, is that they have constant physical and chemical properties. So no matter where you take a piece of that substance, that piece is going to act exactly the same as if you took a piece from the other side. Okay? Now let's talk about mixtures. Mixtures is a blend of two or more substances that retain own properties. Okay? So now a mixture, let's say if I'm adding water and sodium. Now I have one element, one compound, and I'm putting them together, but I'm not bonding them. I'm just physically putting them next to each other. That's making salt water. Okay? So salt still is going to act like salt, water is still going to act like water, but you put them together now. Now there's two different types of mixtures that we have to be concerned with. One is a heterogeneous mixture. This means that it's not uniform throughout. An example I put up here was granite. If you look at a granite countertop, you can see all the different stones in it. Yes, it's a mixture because all the stones are put together into that countertop. But if you were to take a piece of granite from the end of a counter, from a piece of granite in the middle of the counter, you are not guaranteed that those two pieces have the same chemical composition. Now, when we talk about a homogeneous mixture, they are uniform throughout. So again, if I'm talking about salt water, like I was before, if you thoroughly mix salt water, when you are looking at the composition of salt water, it will be uniform throughout it. So if I were to take salt water off the top of a beaker versus the salt water at the bottom of the beaker, as long as it's thoroughly mixed, those two compositions will be exactly the same. Another example of that would be air. If you're looking at air, you can't be like, oh, here's an oxygen molecule, and here's a nitrogen molecule. No, you don't know that. Throughout, all of air is the same composition, no matter where you are, so that is going to be a homogeneous mixture also. So you cannot see a difference depending on what part of the sample you're taking. Underneath homogeneous mixtures are solutions. Solution is just two different types of substances being put together. It's usually in a liquid form, but it doesn't always have to be two liquids. It can be a solid in a liquid. It can be a gas in a liquid, coming together to form a solution. Now we're going to talk about an aqueous solution. It's a special type of solution, so make sure you know what it is. And it just means matter dissolved in water. In chemistry, most of the solutions we will be using are aqueous solutions. And again, that's when a piece of matter is dissolved into water. The last part of matter that we have to talk about is the difference between a physical change and a chemical change. So, a physical change is a change that does not involve a change in the identity of a substance. So, molecules are remaining the same. Some examples of this are state changes and motion. So let's talk about state changes. We learned about the different states of matter, liquid, solid, gas. If we take water, for instance, we have H2O when it's liquid, right? Now, if I heat it up, it's now going to become a gas. We know the difference between a liquid and gas is that the gas molecules are moving faster. But what is not going to change is that it's still going to be H2O. Our actual compound is not changing at all. Same thing if we were to go down to a solid. H2O particles, they're moving slower, really not moving at all, but the actual molecule is not changing. So this can be true if we are breaking something. So if we took a piece of wood and broke it in half, it's still wood, but it's now just looks a little bit different. Cutting something, those are all going to be physical changes. A chemical change is a change that alters the identity of the substance. Once you perform a chemical change, you can never get your original substance back. So the molecules are actually changing, they're no longer the same. So here, if I were to again have water, if it were to go under a chemical change, maybe our hydrogens and our oxygens are going to separate. So now I have hydrogen and oxygen, but it's no longer water because they're two separate compounds now. Now, when we're talking about chemical changes, there can be different proofs in order to prove that we have a chemical change. The The first one is production of a gas. If you see gas, so you can usually see gas when something is bubbling, or if you smell a different odor, that is going to be an indication that a chemical change occurred. Precipitate formation. A precipitate is just a solid that is formed from a chemical reaction. So we're going to do a few examples of this in class, but a precipitate is when you mix two liquids together and a solid comes out of solution, and you'll see a solid on the bottom of the beaker. Energy released or absorbed. Whenever a chemical reaction happens, energy is either taken in or given off. So we could record a change in temperature of the actual chemicals, or sometimes if energy is given off, we can see a light. Lastly, there can be a change in color. That usually pairs up with precipitate, because the precipitate that we form will usually be a different color than the two chemicals that were added together. We have to be careful with changing color, because there's a difference between diluting something and actually forming a new chemical. For changing color, we're looking for a dramatic color change. For diluting something, that is going to be a physical change, and that is going to be, you're going to start off with a brighter color. You're going to add water to it. Just because you're adding water doesn't mean the molecules are changing. You're just making the concentration of something a little bit less.